Right, okay, so Quorum Queues. We started work on the Raft library that underpins Quorum Queues, and now lots of other things. I'm sure you heard the Raft word quite a lot of times today. We started that in 2017, so that's 5 and a bit years ago, which is quite a long time. Yes, we didn't release Quorum Queues per se until 2019, but even that is a long time ago now, right? And maybe there would be, this is a good time. Lots of things, we've learned a lot of things. We've, you know, a lot of time has passed. We've fixed some stuff. And maybe it's good to sort of, I don't know, try to do a bit of a retrospective type of thing. Just go back in time, look at the design, talk some stuff about the design, and maybe then look at some individual aspects of that worked well or didn't work well, or we've still got to do. So that's a radio button. Just it's not that clear when it's that big, huh? So as developers, and system designers, we don't often, or maybe, you know, we don't often get a choice as to by what pieces of infrastructure that we actually get to use in our systems. Sometimes we do, but you know, a lot of the time there's already something in place that's already been used. Someone else made that decision for you. So sometimes you can, you know, sometimes that piece of infrastructure will be RabbitMQ, right? And that's fine. So we learn the API and we learn how to use the SDK for a given language. We get on with writing our applications. And, you know, we can't know everything about the system that, you know, wasn't our choice. Even if it is our choice, we don't know everything about the guarantees that it provides. So we make assumptions, right? We make assumption based on the knowledge that we already have, you know, about what a system will do with our data, what properties it has, what guarantees that it offers. And if we read the docs, or if we had some prior knowledge, or maybe we read Hacker News about something, we might have expectations about what the system will do. Or we may even fall back to hope that the system does the right thing, you know. And I guess I was there, roughly, in 2012, 2013, maybe. I just started a new role. They were using RabbitMQ for messaging. So I learned the SDK, and I started writing application. I was making assumptions. I knew some stuff about it. I had some expectations, and I really hoped that RabbitMQ would do the right thing with my messages, even when, you know, times got tough, when things crashed and restarted, and network partitions and all that stuff. So you keep going like that, and inevitably, when you expect, hope, and assume stuff, you end up disappointed. And I guess that's what happened to me as well. So in 2014, RabbitMQ failed the Jepsen test suite. I don't know if how many people are familiar with the Jepsen suite, but it's basically a suite that sort of challenges the promises that data service vendors provide in their documentation. So in this particular case, the Jepsen suite can test a lot of things, but in this particular case, it tested message data loss. So that's confirmed message data loss under network partition conditions. So slightly contrived tests, but certainly possible scenarios. And RabbitMQ was found to lose 35% of acknowledged writes. So that's messages that were published and had a publisher confirm notification returned back to the publisher. This is not what you assume it would do, right? This is not what you expect, or, you know, I hope no one hopes for it, right? So yeah, I actually felt a little bit embarrassed. I mean, I had no real stake in it apart from being a user, right, of RabbitMQ. I liked the product, I liked the API, I liked what I could do with it, but I really didn't want it to have this fundamental issue. And there's one thing worth noting here is that these were what we now call classic, mirrored, HA, whatever you like, queues, right? Where we take a Rabbit queue and we replicate it. So the counterintuitive thing is that replicating the data actually opened up exactly this scenario. It made your data less safe. And that's really unexpected. Anyway, time moves on. We wrote some system. We still used Rabbit. That didn't stop us. We did some work, some R&D type of work. I personally spent a lot of time implementing Raft back then for a different type of system. I did use Rabbit eventually, but not for the sort of Raft consensus protocol. And in about 2016, I don't know, I guess this thing preyed on my mind, so I guess I applied to join the RabbitMQ team. And I was chatting to Michael Clishin. I'm sure you know who Michael Clishin is. And we didn't talk about whether I could reverse a linked list on a whiteboard, which is a good thing. You could argue, because I probably wouldn't be here. But we talked about Raft, because that's what I knew stuff about. I worked with Raft then for a couple of years. And we talked about using Raft to implement a queue. And we talked about what we would need from a queue, in order to feel less embarrassed. So the primary thing that we needed was not to lose confirmed messages, okay? Because that's what the Jepsen test showed us, that we failed, and that's unexpected, right? But that's actually really easy. I mean, anyone could do that. All you do is just accept lots and lots of messages, and you never confirm anything. So you give no promises, right? No one's disappointed, because we never promised. But of course, that's not a useful system, so we needed some other properties as well. We need a system to have good availability properties, right? A system that can't accept writes is no good, right? So we needed to have some properties of that. We needed to have reliable recovery properties, right? So if you used HA mirrored queues, you might have had queues stuck on syncing. That kind of reduces the availability and makes it feel like something might never complete, right? Makes you nervous. We need to have good throughput. I mean, one thing about throughput is that it doesn't really matter how much throughput a data vendor provides. There's always someone who needs a bit more, right? So luckily, we have an answer now, right? Just use streams if you want more throughput. But it comes with some other challenges as well, of course. We needed to have modern queue features, dead lettering, competing consumers, limits, all those things that you expect from a modern message queue. We needed to have those. We needed to be able to have many of them. If you just can have one queue, you have a scaling issue. So yeah, thousands of queues would be desirable. We needed the code to be maintainable so that we could understand it ourselves and ship new features and still retain safety over the data without sort of risking things. And predictable resource use is good as well. You need to be able to know where your limits are without. Right, so I know you've probably heard lots about Raft today, at least if you attended a certain number of the talks. But just to make sure that everyone has some idea of what Raft is underneath, we'll just do one slide on it and see how that goes. So Raft allows you to implement what's referred to as a replicated state machine. So that means it's a cluster of, in this case, our Erlang processes, which I don't have to explain now, because Lucas's talk and even other talks explain the same thing. In our case, it's Erlang processes that we're clustering. So you have a leader, and you have 0 or more followers. It's a consensus algorithm, and what we agree on, right? That's what you do when you have a consensus algorithm. You have to agree on a value, and the value we agree on is this log of operation, represented here by a table. This log of operations is, in our case, and in most Raft implementations case, always written to disk. Right? So we accept writes on the leader side, and then we replicate the writes to the followers, and the followers reply back, say, yes, I've written it to the log, it's on disk, it's fine. And when we get a quorum, more than half of the members in this cluster of processes acknowledging back that they got the right, then we consider, in this case, we are following index 4. We're considering index 4 as committed. And when it's committed, we take that and we apply some logic, which is, in our case, in Quorum Queue's case, is just the queue logic, right? What happens when a message arrives at the queue, for example. And we calculate the new state, and that's your state machine, right? You take an input, you take the current state, and you return a new state, okay? And we do that on every member in the cluster. So every member ends up calculating exactly the same state because they have agreed on the log and the order of entries in the log. And that's what we get our guarantees from, right? It's the same on all nodes. Right, one more thing about that before we continue. Because when we get an acknowledgement, because when we commit, we know more than half of these members have this entry that we wanted to append to the log. That's when we get our acknowledgement, and that mechanism interacts with the publisher confirm mechanism in RabbitMQ, right? So when you write to a quorum queue, publish to a quorum queue, the publisher confirm only returns after this raft round, okay? And because we only need a quorum to reply before we actually confirm, we can lose a follower without even noticing, right? So we get some degree of failure tolerance, of high availability, if you like, although high availability is a property of your entire system, not just of the queue, right? So I hope that's enough for us to continue with the rest. Right, so we got Raft. How do we make a queue out of Raft? Well, we've already done it, so you can just look at the code. But let's go through some of the design thinking for it. So Consesus has a property that you always need to consider. It's costly, right? Consesus is costly because it involves communication. You need to communicate in order to agree on a value, the log. But that takes time, right? You never know if your peers are going to reply, how long it's going to take them to process your request. So you need to, as a general rule, you should choose very carefully what you use Consesus for. Try to make local decisions, local processing if you can. Now with Quorum Queues, we didn't do that. We put it all inside Raft. Okay? We put all the queue logic and the messages into the Consesus, the replicated state machine. And we did that for a reason. We didn't just do it because it was easier. But partly because it was easier. But we'll see why in a moment. The alternatives are actually really quite complex because they do involve a lot of additional synchronization and coordination between Raft machines, which is something that you also want to avoid when you try to design such systems. So we get some stuff for free with Raft. Some of those requirements that we wanted to have from our new queue type. Just by having Raft, we got them for free. I mean, obviously, it's extremely expensive to write a Raft implementation from scratch. It takes a lot of time, a lot of resource. But once that is free, you kind of get a degree of message safety, right? You get very strong message safety guarantees just from the properties that I just explained. By putting the messages into this Raft log, they are replicated, and we don't get a confirmation on the client side until we know they're replicated to at least a quorum of the members in your Raft cluster, right? In your Quorum Queue. And one thing I didn't mention is that we also put fsync on the path. So fsync is the means by where we tell the operating system that we really like it to actually flush the data to the actual underlying storage and not just keep it in the page cache. Sometimes some file systems they don't meet your expectations and assumptions about that, but most modern ones do, so that's good. With Raft, we also get reliable recovery. Because all we do, there's no special thing that we need to do when we're recovering. We just read the log from the beginning to the end in order to recalculate that state that we were talking about, the queue state. And we get availability, as we said. We have a quorum. And this is combined with a leader election process, which is based on the freshness of the log. So if a leader goes down, only a follower with the most up-to-date log will be considered for the next leadership, which means that that combined with the quorum properties means that a leader can't be elected that doesn't have all the committed entries in it already. Right? So we won't lose any messages just because we had to elect a new leader. Right? And that's exactly what happens with classic HAQ, actually. It's part of the leader election process. As the leader elect a new leader that doesn't have all the messages. This is just a graph from the Jepsen test suite. We obviously run the Jepsen test suite now internally, continuously, in order to test that that the promises that we've been providing over the last few years actually still hold true. This one is relatively interesting. These gray sections are network partition events, so time goes left to right. In this particular one here, the leader of a quorum queue got partitioned off, so it's in minority. And you see a little dip in the blue sort of bands of successful operations. That's the time it took to elect a new leader. So not very long. Okay. And if it's a hard crash, it's much, much quicker. We detect that almost straight away. So we can tick off a lot of the boxes that we wanted from a queue, just from having Raft. So that you can sort of kind of see now where we wanted to put it all into there. If we don't put it all into there, we only get to tick off these items against what we put in. They've put everything in there, we get a lot for free. So I think that's that's the main reason why we did it this way. It does come at some potential downsides. So Michal and David kind of talked about this a fair bit. A queue, even though it is a replicated queue, it's still a single thread of computation, right? It's a single Erlang process in terms of executing the logic, even though because we do the same thing on all the nodes, right? So if you're publishing very quickly and you add a consumer, your publishing rate will go down. Like you're publishing a single queue, you add a consumer, because all of a sudden you have to share the amount of work that you can do for this single queue. And I think we've said it a few times during the day. The solution is the same as it's always been: distribute your load across multiple queues. So nothing new there. So one thing we did get wrong, though, is that initially we have the messages in the log, right? We have all the operations we want to perform on the messages in the log. But we kept the messages in memory initially. We thought we needed that in order to provide the kind of throughput that we wanted out of the system. which kind of makes sense. You don't want to go to disk to read a message. But after quite some time testing this, although some scenarios were a little bit quicker, we got much more unreliable performance whilst keeping messages in memory. And we started really sort of affecting the amount of garbage collection and stuff it needed to do. So we removed that option completely in 3.10, and everything is quite a lot better. All consumer deliveries are now read from the Raft log, okay, when there's time to deliver them. Oh, one more thing to say about that is that part of the Raft log is actually cached in memory anyway, so it's very rarely for an empty Quorum Queue that you ever have to read anything from disk, right? But we keep a very hard control on the amount of memory per node that we keep in that cache. Right, throughput versus having many queues. So yeah, that was a bit of a fight between those two requirements. When we first implemented it, we had each Quorum Queue have its own log file and writing to disk itself. But using the kind of sort of standard network attached storage type of drives that still are in use in many places, we quite quickly noticed that adding even just like 10 Quorum Queues, the amount of latency we experienced in the fsync operation just started sort of going up, and it's contention on the disk at the disk level. So in order to fix this, we introduced a write-ahead log process into the Raft library, which does centralize all the writes that come in for all the operations for the Raft system. So it does heavy batching inside a single Erlang process, and then fsyncs, and then reads another batch, and then fsyncs. And we can get really good throughput with that, but it does reduce the amount of parallelism that we can sustain. But it was more than enough to meet our initial sort of throughput expectations. We wanted them to be at least as good as the classic mirrored queues with durable messages spread across the same number of nodes. I think if you watched the previous talk, you would have seen that it probably met those expectations. There are modern disks, NVMEs, that does better when it comes to the amount of parallelism. You can actually push down the actual disk. But not all systems are guaranteed to use them, right? Not all system wants to use them. We still need to have this centralized point. What we have experimented with is to sort of shard the load and still have multiple of these write-ahead logs in order to scale further. But we tested it. It made some potential benefit, but there are other optimization points before we get there.
So those are blocking batch writes as well?
They are blocking writes, yeah, but they are on a different process, so they don't block the queue process. The queue process can keep working.
And how about data loss then, if something crashes there?
You won't get a confirm until that operation has completed, fsync has completed, and it's been done on a Quorum nodes. Okay, so the properties are still the same. The work is just done elsewhere. Right, so here is something that sort of is in the throughput resource use kind of thing. We call it local delivery. Kind of just makes sense, really. It's nothing special, but that's not how it worked before, so that's why it's worth mentioning. So because we calculate exactly the same state on every member in a Quorum Queue cluster, rather than delivering messages from the queue leader to a channel that is on a different Rabbit node, if there is a follower on the same node, we just deliver the message from the follower, avoiding the network hop from the leader to the channel process that is not on the same node. And just uses less network. and also spreads the load of reading these messages from the log across multiple nodes instead of just from the one node. So it does sort of gives us a little bit of parallelism when it comes to consumption, assuming you have more than one consumer. Otherwise, it doesn't do an awful lot. But really, because the state is deterministic, we can do that. If it wasn't, we couldn't do that. We probably couldn't do that with classic mirror queues because they're not guaranteed to contain exactly the same messages if they've been recovered. Right, maintainability. Putting all the queue logic in one place has one benefit in that it's sort of one place where we can test that queue logic. Raft state machine logic tends to be, it needs to be deterministic. So the easiest way to make it deterministic is by only using side effect free and pure logic when you calculate your queue state. So that means we won't look on the network, we won't look at the current time, we won't look on disk or anywhere else apart from the data we pass into the function, which is the entry that is in the log and the current state. Those are the two only things that we use in order to calculate the output state. Because if you looked on the network or the current time, right, and then you restarted your quorum queue and then reread the log to try to recalculate the same state, it would be a different time, right? It would be a different result, and we can't have that. So this also makes it easy to test this logic in isolation, and we got an extensive property suite for it, which caught so many logic errors. I mean, it's really been beneficial. And it's very easy to write one because hardly any setup, it's one module, one function, lots of expectations. But how can we fix bugs if we have to have deterministic logic? So we can't change the logic, right? Because that would make it non-deterministic and won't be the same output if we have to restart or if we do a live upgrade where we restart one node, the queue moves on, one node might have a bug fix, and it will calculate a different state. So that was a bit of a problem, but a bit of thinking. We came up with something we call machine versions. This is a feature of our Raft library, not Quorum Queue specific. It's a way for us to sort of switch to the new logic at a specific point in the log. So it's a command. Effectively, you can think of it as a command in the log. At this point, all members should switch to the new logic. Before that, they should use the old logic. That does mean that we have to keep all the logic. So it does mean a bit more ceremony. If we want to fix a bug, yes, there's stuff we need to do. If we want to add new features, there's quite a lot of things we want to do if we want to refactor things. But it does allow us to retain the deterministic property and not sort of mess up the logic between different members in the cluster. Yes, so if you look in our source code directory, you can see all the code since 3.8, 3.9, 3.10. Yes, so we're on version 3 at the moment, internal version 3. So we started on 0, 1, 2, 3. We're only on 3 with version 3.11 because we needed to fix a bug. That's the first time we incremented the machine version just to fix a bug. All the other ones have been to add new features to Quorum Queues or to change it to fit within within some other change. Just a feature worth mentioning. Quorum Queues have delivery limits. It's effectively a poison message handling strategy. So what RabbitMQs haven't done historically is keep track of the number of times they've been returned to the queue. So typically that would be a consumer failing to process a message and crashing and returning it or returning it explicitly. Now you can put an upper bound on that. And that's something that's been working very well. It's something I wanted back when I was a Rabbit user. And I even was in contact with the Rabbit team at the time, and they said, yeah, we haven't got time to do that. So when I got the chance, I did it. So that's one way to get your feature in. Join the Rabbit team and then implement it. Yeah. Right, so the message gets removed or deadlettered whenever the limit is reached. Right? It's very simple. It's not, it's just a counter. That's all it was. You can see the current count in your messages by inspecting the X delivery count header. So it won't be there for 0 if it's the first delivery, but after that, you will be able to see that header and keep, you could even do some logic in your client applications with that if you want to. Do use this feature. It's really is good. I mean, for overall system stability. Right. So this is not really a feature. It's more of a feature limitation. So at some point we had to pay, right? We got all this stuff for free, right? But there's no free lunch, right, really. There's always, you have to give somewhere, right? So you might have seen this section in the Quorum Queue documentation. I assume everyone has seen it. No? You didn't read that far? It's at the very bottom? No? Okay. I know some of you haven't seen it because I've had bug reports. Repeated requeues. So I'm not going to explain exactly why we have this limitation. We have this limitation, and it's a limitation that came from Raft, came from the way we needed to, do snapshotting in order to truncate the log. I do explain it in my 2019 talk at this very same conference, if you're that interested. But basically, it means that you can't continuously reject a message to a queue, because every operation that you send back, and rejecting a message, even if it's a small operation, it's an operation, right? And the operation goes to the log. And the log goes to disk and uses up disk space. So if you sit in a tight loop, doing requeues, like say your database is down, but you don't have a delivery limit set, and you just keep doing this, yes, you will run out of disk eventually, probably. Okay. And this didn't really pan out, because a lot of sort of failure handling in some Rabbit sort of messaging libraries and stuff is very simplistic, right? So consumer processing fails for some reason, the error is caught, try catch, and returned with requeue equals true. When we requeue a message to a Rabbit queue, we try to put it as close to the front of the queue as possible, right? Depending if there are other requeues as well. But that just means that the message is just immediately going to be sent back to the same consumer or another consumer, but there's something wrong, right, with the processing of this message. So the likelihood is that it's just going to fail straight again, and we just do this a lot. Now, I kind of wanted to sort of enter a diversion here about consumer failure handling, but I don't think I'm going to get quite enough time. What I wanted to say about this feature is that from 3.10, if you don't have a delivery limit set, we will now return your message to the back of the queue in a way that means that we can still truncate the log. So we needed to handle this. It's not a perfect solution, because a perfect solution would be to keep the original behavior, but this is what we do now in order to avoid a scenario when you run out of disk, which is worse, right? And I can give you an offline justification for why that's totally acceptable with the guarantees that we have with the queues we have. But I wanted to talk about this one. That's why I'm skipping the consumer handling. Dead lettering. So that's been a feature in RabbitMQ for a very long time, right? And it's quite heavily used, popular. Quorum Queues, I've had it since the beginning. But one thing that most people probably don't assume, expect, or even hope for is that the guarantees to move messages between queues in RabbitMQ is at most once. So they will be delivered, but when you dead letter, you move from one queue to the other 1 or 0 times. That's not what you want, right? Is it?
You lose message.
Pardon?
You lose the message.
You could lose the message, yes. All right, yeah. Yes. Yeah. So, since 3.10, you can now configure quorum queues to dead letter messages with at least once guarantees. So, one or more times. Typically only one, but if things go a bit shaky, you might get duplicates. So, that's why it took some time for us to implement message TTLs, because I know that's what you use message TTLs for, right? You use it from delayed retries. That's what most people use them for. You reject without requeuing. The message gets dead letter to another queue. That queue has got a message TTL set, and it returns it back to the original queue for processing in 15 minutes or whatever, right? That's a common use case. But we didn't want to implement that until we could implement at least once guarantees for dead lettering, right? Because otherwise we couldn't give you these guarantees for quorum queues, right? We couldn't meet the expectations and assumptions of people without sort of this substantial piece of work, which it was. So, thank you for staying patient with that message TTLs. You got them now. They're also in 3.10. Oh, yeah, here they are. I explain that. Right, okay, there's some features that consider missing. Priority queues, we don't really do that. Very similar reasons for why, if you think about it, priority queues is basically dividing up a queue into multiple queues, right? And if you only process one queue, you're going to have messages left in the other queues potentially forever, right? If you only process high priority messages and you always have a backlog of high priority messages, that's all the work that consumers will do, right? That won't work with quorum queues. Quorum queues wouldn't be able to handle that. That's another one of those limitations, the same limitation as the return with requeue, right? But we could possibly implement a priority queue that's a bit looser and processes from all priorities, but just a bit more from the higher priorities, right? A fairer sharing type of queue rather than a hard priority queue type of limit. One feature that's missing, in my opinion, is publisher message deduplication. It's not 100% clear that it's definitely a queue feature or a feature of the system, but if it was in the queue, it's missing. And that will allow you to avoid deduplication when you need to retry publishers that you don't get a publisher confirm for within some time frame, right? Right now, you would have to sort of implement your own retries and get at least once guarantees on the ingress of the queue as well as on the output, right? I just added this because of discussion earlier. Disaster recovery. So you can recover, once you lose a quorum, you can recover the data that's in the queue. That's still to do. Totally doable, and that is very likely to happen. In the future. Where are we next? Skip that. Right, so yes, keeping the entire queue state in Raft adds some complexity, but also some opportunity. Local delivery is something that we couldn't do without doing this. We miss out on some features because message sharing, for example, that classic queues can do if you have larger messages and a fan-out pattern, they only store the message once and they just keep a reference to the message. We can't do that with quorum queues because then you wouldn't get the guarantees over the message, right? The message would be outside of the queue and all of a sudden you lose all the guarantees. So we want to keep the guarantees, so we'll have to copy messages if you do fan-outs. So don't do too many fan-outs with quorum queues. Additional ceremony for bug fixes and features hasn't proven too bad so far. We've managed to ship quite a bit. And we got lots of stuff for free. We got safe messages, we got availability properties that I personally think are quite understandable, right? Quorum, you can lose, you got 3, you can lose 1. You got 5, you can lose 2. It's quite easy to reason about. Reliable recovery, there's no real recovery in place, right? You just read the log and you continue log replication where you were. It's not really a special thing, it's just normal. Decent throughput, again, always, more is always welcome, Michal, yes? Yeah. We can have many queues. Some people have thousands of these. It seems to be working okay. We got most of the features of classic queues and a few that classic queues don't have, like Poisson message handling and at least one state lettering. And reasonably maintainable code, but I guess I wrote a lot of it, so I should say that, right? I don't know if you have to ask my colleagues. I don't know. So, right, so with Quorum Queues, I don't just hope, I expect that we can deliver on the majority of the sort of assumptions and expectations, and maybe even some of the hopes of users that are using RabbitMQ, and the kind of expectations they have of a modern message queue in these days, right? Okay.
Okay. Do we have any questions for Karl? There we go.
Hi, I'm curious about your Rafts implementation. Did you implement the algorithm exactly as it's described in the original paper, or did you make some modifications to it, as I know some implementations tend to do?
Yeah, it's pretty straight on, actually, in terms of if you look at it from a sort of if you squint a bit and don't look at it too closely. Yes, I mean, we had to innovate some things like machine versions, and we had to introduce this write-ahead log, I said, in order to have many, so multi-raft, if you like, right? Raft is like described in the paper as one server, one thing, kind of thing, and we have thousands, so we needed to make some changes around that. But apart from that, it's pretty straight on, yeah.
I have two hopefully quick questions. So since, I appreciate, as someone who has a lot of queues in our clusters, I appreciate that y'all did prioritize, being able to support many queues. So first question is, is it comparable to, classic mirrored queues in terms of the number of queues that you can support? And my second quick question is, just because I know of like one particular use case that really wants to use message priority to solve a big problem, how likely are y'all to add even like the soft priority, like queue priority queue support in Quorum Queues?
Okay, so the first question was, is it comparable? Right. I don't actually know. I know we can have thousands. Is it comparable once you start running them? I mean, maybe that's where we sort of compare better. I'm not sure. I think the best way, I mean, I don't know if you went to the talk about performance, there's lots of tooling available to you to sort of run your specific scenarios. And if you find things that are, that it can't cope with, share with us. We want those scenarios for sure. The replication protocol of classic mirror queues is inefficient. It actually duplicates a message on the network, right? So, and we don't do that here. So yes, I think we'll do better there. But testing is the only way. Yeah. And so, how likely are we to do priority queues? It's not penciled in. I think it's probably surprised all my colleagues that I said we might do it. That probably tells you where we're at with that. But it could very well happen. It's being requested a lot, right? And that this is one more, right?
Do you have any other questions?
Did you ever consider to use any other consensus algorithm than Raft?
I'd already done Raft once, so no. That's my hammer.
So it was set from the start.
Yeah.
Anyone else? Do we have any questions online?
Just quickly then, I saw you were using fsync. Did you consider using direct.io?
Direct.io sort of puts a few more constraints on on how easily you can implement that. Yeah, we've experimented with things, but firstly, the Erlang API doesn't support direct I/O at the moment anyway, so we can't. I know a lot of other data services like Red Panda does direct I/O. We might experiment with that. Right now, I think we would like to try scaling the write-ahead log instead, and in order to sort of better saturate the disks. Yeah.
And on that subject, have you tried different file systems, different options that you'd recommend, one above the other, X4 with no A time, or I don't know, if you've got anything?
I can't for sure recommend one, but I know someone who could test that. I think they're going to be roughly equal, all the modern ones, right? I recommend a modern one. ext4 is what we tend to do most of our testing on.
Okay, so we have some questions online. Dimitri, do you want to unmute yourself and ask Karl a question? You can't, okay. So to get perf benefits out of QQ, if I get this right, I need multiple consumers. How does this affect the order?
You don't need multiple consumers. You need to split your workload across multiple queues, right? And one feature I didn't mention, which I think is somewhat underused, but it does have downside, is the single active consumer feature, where you only have a single, well, actually it's in the name, is you have a single active consumer at any one time, and you can have any number of backup consumer which will take over if that consumer crashes or unsubscribes. So if you have a single active consumer, you can see the input order of the queue, right? So whatever is in the queue, you will see messages in that order. Even if you use a prefetch, if you start returning messages to queue, they become unordered, right? But as long as you sort of keep that order and process messages in the order you receive them, you'll see the input order of the queue. Of course, you might see duplicates, right? That's why we're talking about message deduplication for publishers, right? If we had that, you would get pretty good ordering, but yeah.
Okay, we have another question from Johan. If you unmute yourself, please ask.
So, are there any plans to run the Jepsen tests officially again to update from the 3.3.0? And maybe this was already answered in the screening session, but to run that with screens too.
Okay. Right, so officially would mean to engage, Kyle Kingsbury is the person behind Jepsen, and he's no, I don't think we have any immediate plans for that. One of the reasons for that is Jepsen doesn't just test data loss, right? If you engage Karl, he will test availability as well. And right now with Amnesia, right, we have some downsides, right? Amnesia will disconnect nodes, not Amnesia, but what we layered on top of Amnesia in order to try to get classic mirror queues to work. With Kepri, if you saw that talk, we should be in a much better position to actually sort of officially test the whole system and the sort of availability properties and data properties guarantees that it provides under really sort of harsh conditions. But we do run the exact Jepsen test suite in our CI environment on every release and commit of RabbitMQ. We have extended that suite to include a lot more sort of scenarios and stuff like that, and it is passing. It's just not public. We don't want to use it as a marketing tool or anything like that. It's something for us to know that the things that we say hold true to the best of our abilities.
Thank you for that. We have another question online.
Sure.
Apologies. V. Hong, do you want to unmute yourself and ask that question?
Yes. So you mentioned that there's a missing feature for disaster recovery. And does it mean that if you permanently lose the majority of the nodes, you permanently lose the queues, even though the data is still in the minority node?
Right, so I didn't quite catch all that, but I think, so right now, if you lose a majority of your nodes, so all your disks rather. I mean, that's really the disk data that we're concerned about, because you can always spin another node with the same name, right? Yes, right now the queue will be unavailable for processing. That includes reading from it or anything like that. So disaster recovery in this context would mean a special command that allowed you to force that queue to start anyway as a single member raft cluster or something like that, and then you could sort of take it from there. But if you lose 2 out of your 3 nodes permanently, you're having a really, really, really bad day anyway. It's been out since 2019, and I don't think that's happened to anyone. At least they didn't tell us. So.
Okay, I think that's it for questions. So thank you very much, Karl Nilsson.